How did anybody look at the homework solutions? I just did them in MATLAB to hopefully make it easy or easier to follow. Did anybody take a look at the homework solutions and see how theirs compared? Nobody? You didn't have to. It's just like you can check your Jacobians, check your power balance equations, kind of check those because I know, you're prone to, or not you, but one is prone to error in making those. And so sort of the meticulousness of being able to write those is pretty important. And so what I've done that's helped me to be able to figure out how to write those equations is really just be like, lots of paper. And at the beginning, when you're writing delta, let's say delta P2, you always let I equal 2 to kind of give you that memory that I is going to be equal to 2. So anytime I see I, I'm substituting there. So kind of sort of highlight that because it's easy to mix up the I and the K because they are so close. And then usually putting in the K is not so bad as long as I have the I specified well out saying, okay, this is the position. So usually that helps me just to do the power balance equations is to identify what the I variable is and then just walk through the Ks. After that, the partial derivatives can be a little bit confusing. I had a student, a different student was asking me like, how to do the chain rule a little bit because you don't do that in calculus all the time, right? So you forget the cosine of theta 2 minus theta 1 with respect to theta 2 is going to have the sine of theta 2 minus theta 1 because of the chain rule, right? And a lot of you just forget it because how often do you do derivatives like that, right? It's not that common. So the one thing that I can say that helps me really go through those is simplify, simplify, simplify. The fewer the variables you have, the less prone you are to making a mistake, right? So when you're doing those equations, you can write out the full, 100% equations with all variables. And if you see some of the homework problems that I've been doing or some of the examples that I've done in class, I have, exhaustive, gory detail, including all parts of it. But that takes a lot of practice to be able to get through those. And, again, you're prone to make mistakes. So the idea is if you can simplify, because you're probably not going to be writing MATLAB code or any kind of code that does load flow analysis. Most programs, you'll have to purchase those. If you're trying to write code to do that just to get through a problem, just get through the problem. Don't spend a lot of time making it generic because otherwise you're going to just find that it takes a lot of time and it can get really confusing. Now you can automate it. And so the equations we have is you can set up while loops or for loops for I equals 1 to 7. That's like your end loop. And then K equals 1 or I equals 1. And then you can just go ahead and parse it like that. But, that takes a level of coding, at least in MATLAB. That's not hard. It just might take a little bit more expertise than perhaps you may have. And certainly more expertise than I expect because MATLAB is a calculator in this class, right? We're not MATLAB coders. We're just using it as a calculator, which leads on to the first discussion, right? Which is our exam on Monday. Going to be right here, 1 to 350. We got to end at 350 because people might have class at 4. So I can't extend it and let people go because not everybody has the same opportunity. And again, we're trying to be equitable and fair, which means if you have 2 hours and 50 minutes, or if they have 2 hours and 50 minutes, I can't extend it unless you've got a note from the folks over in disability services to get additional time. I can't extend it for you just because that would not be fair. So make sure you have that time set ahead. If you are going to do it online remotely, that's okay too. Make sure your camera's up. And it does give you a little bit of pinching of your time only because you have to include additional time to get your document uploaded, scanned and uploaded into Brightspace. All right. That's the sort of the important aspect of it or the important part to make sure you include on that when you're actually doing it online. And then the last key thing that I would say is MATLAB is a calculator. If you just hand in a script with no work, you get no credit. Okay, just so that there's no confusion. I don't want people to say, well, I get the answer right and the MATLAB script is perfect and yada, yada, yada. It's like, but I don't know if you did that or if somebody else did that. I can't tell what you know. That's MATLAB is doing that. So it's not clear to me, what part of that is done by you and what part of that is done by somebody else. So MATLAB scripts are not acceptable to show your work. You've got to show your work on paper. And then if you want to do, include the MATLAB script. I don't have an issue with you using the MATLAB script or supplying it, but there's a very low probability that I'm actually going to look at it because again, I don't need to see the MATLAB script to figure out what's going on. I'm actually going to follow your work. And one last thing, if the last thing that I would recommend is like anything else, if you can make your submissions neater, easier to follow, that makes it easier for me to grade. Sometimes I have to hunt around for stuff. And if I can't find what I'm looking for specifically, I can't spend 30 minutes on a problem. I've got 40 plus students in this class and 6 or 7 problems. It would take me 6 months to get through the grading. So it's got to be clear for me so I can follow your path. You got lots and lots of scratch paper. I'll bring plenty of it. So make sure that it's clear. And for stuff that isn't, you're like, if you're going through it and you've got it on paper and it's not clear, just go ahead and rewrite it. Most of you all will have lots and lots of time to be able to do the test. So there's no reason for you to be like to turn in something that is all hodgepodgey. Just spend the time to kind of do it over. And that's also a great opportunity for you all to check your work. Did this make sense? Did I follow what I expected? Am I getting the right answer? So that's a nice way to check your work. Question.
Would you want to see us doing out every partial derivative, or is that step small enough that we can just use calculate for? So like we show the setup of what partial derivative should be, and then we just write the partial derivative without showing you all the steps we go take.
Well, I guess I don't understand how you'd use your calculator to get the partial derivative. You have to do the steps on paper to get the partial derivative. So what do you mean by having your calculator give you the partial?
Can you input a function and then have it take the derivative with respect to whatever variable you want?
You can do it symbolically, but again, I don't want anybody done it symbolic. So I guess what I'm saying is I'd like to see enough work for you to show that you did the partial derivatives by hand.
Okay.
Yes, sir.
In MATLAB, you can write Jacobian to the function. If you want to do later one, you do the Jacobian.
It'll actually give you the equations, but you got to do is
Just
the numbers.
Numbers.
Yeah, I don't want to see numbers, right? I want to see actual what your Jacobian is.
Oh, okay.
I don't want to see numbers. I want to see equations. Okay. You can do it symbolically too. MATLAB does have the capability. MathCAD can do things symbolically. But again, I'm not expecting you to be derivatives. It's really just, do you understand the process well enough to get it and go from there? Correct? Yeah, so we're not relying on computers to do this for us. We got to be able to do it. Okay? So that's the high-level test stuff. What are we going to cover? Transmission line equivalent. Been a minute, right? Pi equivalent for our transmission circuit. And so we came up initially with any transmission line has some inductance, resistance, and some capacitance to ground. And we saw that that's not the best representation. It's usually much better to distribute the capacitance on either end of the line and then go ahead and represent the Z in the middle. So just like the Greek letter pi, you have a sending end and a receiving end. The receiving end usually is what dictates the parameters. So normally that's your reference. And then the sending end has to be adjusted accordingly to deliver whatever is expected at the reference. Remember, the reference folks are paying the bills, so you better provide a quality product or else they're going to shop someplace else. We got a lot of the parameters, the Z, the Y/2s. We got those all from the different parameters where we had gamma, the characteristic impedance. We had all those different ones. I'm not so interested in a lot of that stuff unless we're looking at our lossless transmission line. Lossless transmission line means R is going to equal 0. And it's okay usually to do lossless transmission line approximations because usually your resistance is so much lower than your reactance on your transmission line that you can neglect it and not have really that wrong or that off of results. So if you do have a lossless transmission line, your characteristic impedance is just a square root of L over C. Your omega terms and J terms divide out. And then once you do that, then we can do that surge impedance loading, which is, again, really useful for us because most of us in this class aren't going to be doing heavy duty analysis, but we might want to be able to figure out some general operating parameters. For example, I have a transmission line. What loading can I apply to that before my line starts consuming bars, or under that value before it starts supplying bars? So if I'm a system operator and I'm looking at the load on my system and I know that surge impedance loading, the SIL, that's calculated from my characteristic impedance, then I can start to say what other activities that I need to do or will I need to do, right? Because you're trying to predict, you don't want to operate after the fact. You want to try to anticipate and make sure things don't get too murky before you make a change. So you can actually use this to say, well, this is the line parameter. Where above this, I'm going to start overloading it to the point where I need to start injecting reactive power. Or under this level, I'm going to start absorbing reactive power. And both of those can be negative. Overly drawing reactive power means your voltages tend to go really low, and you have to do a lot in your system to increase voltages to that plus or minus 5% nominal. But the other end is bad too. If you're underexcited or under the SIL, I should say it's a better expression, the concern there is that your voltages float too high. And which one is worse? They're about the same, right? If you have a hot system, voltages are too high, you can potentially damage some equipment. Under operated systems, you can damage equipment because you have to pull too much current to be able to supply the load, right? Remember, our loads are fixed power loads, not fixed impedance. So if you drop the voltage, the current's got to go up. Where the overvoltage condition, the current drops down, but now you're pushing devices above, perhaps above their nameplate ratings for voltages, and then you can get some serious issues happening there. So using that SIL really, really helps us go ahead and determine, am I eating or supplying bars, absorbing or supplying? Then we did our hybrid two-port parameter network to introduce our ABCD parameters. Hybrid just means that the units inside the ABCD parameter are mixed. We know that A is going to have the units of nothing. It's a unitless quantity. B is going to have the units, B has the units of ohms. C has the units of mhos, right? The inverse of ohms. And D is a unitless quantity. That's why it's the hybrid one. And we're going to typically use the medium length line parameters because it's much easier and you're going to end up getting more accurate results. So if you have a short line, less than 50 mile, but if you have enough parameters to go ahead and calculate the ABCD for the medium length line, go ahead and use it. Don't try to skimp out and try to use the short line. Don't get yourself in a lot of problem. If you have a long line and you can use the medium, in general, at least for this class, that's going to be okay. And the reason being is because we're not experts at doing hyperbolic sines and cosines, right? When I talked to the class, when we introduced those concepts of hyperbolic sines and cosines, I asked, how many folks of you had been exposed to hyperbolic sines and cosines? I don't think anybody said they had been exposed to hyperbolic sines and cosines. I may have misremembered, but it's not a topic that typically is covered. So we're going to spend most of our time looking at systems using medium length lines. And the worst thing that'll happen is on a short line, you just have slightly more accuracy. That's okay. But here are ABCD parameters, and the ABCD parameters are all based on Z's and Y's based on the entire length of the line. So if you have an 80-mile long line, that Z and that Y is the equivalent impedance for the entire length of the line. And so these are things that you should just put on your sheets, right? Just put those parameters on your sheet. If you don't know, or if Y over 2 sorry, let me back up. If you have a medium length line, it looks like this. Y over 2 here, Y over 2 here, and Z. If it's a short line, all you have is this. These equations will kind of sort of still work for us, right? So what does Y over 2 equal if it's in this case here? Y over 2 is going to be equal to what? Going to be equal to 0, right? Because the impedance of an open circuit is infinity, which makes the admittance equal to 0, right? So if I plug in 0 over here, goodbye and goodbye, right? I have 1 and Z. Isn't that what we have for the short line models? So if you write those equations down and just recognize that Y is equal to 0, all the equations will work out for you. All right. So you don't have to write down a second set of equations to saying, all right, A, B, C, D, because A and D equals 1 and B equals Z and C equals 0 for the short line, correct? I can get that information just by substituting in Y equals 0, right? So just simplify your work. You don't have to have that additional information. When you're doing calculations, remember this is a single phase. I'm using that expression really carefully or with a lot of emphasis. Single phase representation of the transmission line. So when you do your analysis, all your quantities have to be single phase values. All right? Especially if you're doing them as actual quantities, meaning volts, amps, ohms. If you do it in per unit, it makes it so you don't have to worry about that. But if you're doing it with actual values, you really got to be mindful of the fact that you've got to convert everything to single phase. Most of the time, that means dividing by the square root of 3. Your voltage is by the square root of 3. Do not forget the square root of 3. So highlight that fact. Here it is. Highlight that fact, because that's a very common mistake. A bunch of folks did that on the test. I want to see square root of 3s there. I'm not super duper worried about the phase shifts, because remember when we go from line to phase or phase to line, depending if it's a Y or delta, you actually can introduce a phase shift, but you don't need to worry about that here because you get to pick the reference of what you want. Your reference voltage is going to be at an angle of 0. Doesn't matter if it's line or phase, you're picking that value. So it works out in the wash. You don't have to worry about phase shift for shifting between line and phase voltages. And then once we did this, we saw, and then hopefully you've been seeing it in your load flow solutions, that your power flow is almost, you can almost tell exactly where the power flow is based on looking at magnitudes and angles of the voltages. Real power flows from a higher angle to a lower angle, and reactive power flows from a higher magnitude to a lower magnitude. That is applicable if the X over R ratio of your system is pretty high. And all but the problems that we've done in class, except for your homework problem where you had a Y bus that had real parts, all those cases where X, there was no R value. So it was definitively there. But even in the homework problem, homework number 2, you found that that's where you got a higher value, right? You got high enough value so that it would work. And that is all of our basic transmission line stuff, the focus. Remember, the whole reason for doing transmission line is we've got to come up with circuit models of our system. And that was the last piece of the puzzle that we had. We did not know what the equivalent circuits were for transmission systems. So we needed to add that line. Now we've got everything. We got motors, generators, transformers, and transmission lines. So you can fully analyze any power system unless it's got a lot of nonlinear stuff in it. And even then, most people, you can make some efficiencies or make some assumptions about it to simplify. And then the last thing that we did, right, which was kind of a long topic, but hopefully you all see why it takes a long time to get through the material, is the Newton-Raphson load flow. Before we could do a load flow, we actually had to explain how to solve a nonlinear equation using the Newton-Raphson technique. And we have the technique, but then we had to figure out, okay, what's the process we're doing? We need to identify the equations that need solving, which is kind of crazy, right? You sometimes don't even know what equations that you're trying to solve for. Perhaps somebody's given them to you, but in our case, we have to write our own equations based on understanding the system. So knowing what equations we have to write will help us be able to check if our solutions are correct. That's another thing about Newton-Raphson or nonlinear in general. How do you know if we have the right answer? We plug it back in and check to see, does our result come out as expected? If it doesn't, then you got to keep iterating down. So that's why I say we validate them. And what we're doing in this class is we're doing root finding. Root finding means we just set our equations equal to 0. And once that equation evaluates to 0, we're good to go. We've got a valid solution. We also need to identify the variables. In power systems, we kept talking about those as the state variables because they define the state. But we need to figure out what are the variables we don't know, which sounds, again, kind of crazy. It seems like you should know, But we looked at a couple examples where we had power flows in and out of buses. We had voltages specified in and out of buses. So there sometimes is more information that is there because maybe somebody at one point in time measured all those parameters and thought it would be helpful to mark up a diagram and send it to us. In reality, we need to go ahead and figure those out. Then the next step, just as this the plain old Newton-Raphson algorithm, not necessarily specific to load flow or power flow, is now we've got to go ahead and pick a starting point, our initial guess for our variables. Because if you remember, when we did our first example where we had one equation to solve and it was nonlinear, it was x squared minus 2 equals 0. We ended up, if we picked the wrong starting point, right, or not the wrong starting point, but a different starting point, we'd end up with a different solution. One was a square root of -2, and one was a square root of 2, and then the other one, I think, was a negative square root of 2, right? Either one would work for us. So having a starting point is going to help us be able to come to a solution that is viable, okay? Because you can have multiple solutions that are valid. You just don't know if one of those solutions, or any of those solutions for that matter, are going to be viable. Can they physically exist? So we have our initial conditions, and then you can really kind of pause right here, right after step C, because if you identified your initial conditions and if they work, why would you do any more work? So the work that you do is you plug those initial conditions into your equations that you're trying to solve for to see if you get the right answers. And if you get the right answers, you don't need to do any more work. If you were perfectly guessing all of the right answers, that'd be pretty impressive, right? But you'd be done. No reason to do Jacobians because you have the answer. Most likely you will not have the answer, right? Because if you were that good, you would, I don't know, you'd be owning the power system for all intents and purposes because you can figure it out as you go. But in reality, we're probably not going to have the right answer. So at that point, we need to do the sequential linearization, which means we actually have to find the Jacobian. And the Jacobian is our partial derivative matrix. A lot of you all struggled with identifying which partials to take and where. Remember, when we specify our Jacobian, you have to show what your rows are and then what your variables are, so that when you're setting up and taking your partials, then you can just look and see rows, columns, what am I doing for partials? Okay, that's another nugget that I tried to give you, which is like, I would struggle when I was first learning this material, figuring out how to do partial derivatives. But in reality, when I set it up in that matrix, it's much easier for me to see. I don't have to guess. All right. So identifying which partial derivatives you need to take is also part of the process that you need to do. And then once you have the whole method set up, you update your x values based on the equation that we have here. You check again if your f of x is 0. If it is, you're done. If not, you got to rinse and repeat until such time that you get your f of x equals to 0. Or, if you all remembered in MATLAB, what was the thing that I suggested when you did your while loops in MATLAB? For those of you doing your calculator, you do it automatically, but what would you do in MATLAB?
Make maximum iteration.
Yeah. You hit 10 iterations and nothing's changing. Goodbye. I'm done. I'm not just going to keep running my head into a wall. Same thing if you were doing it in a calculator. If you did a calculator and your first iteration result was like your f of x was like 0.1, 0.2, and 0.3, and then the next iteration you got was 10, 20, and 30, would you keep going? It's supposed to go to 0, right? You went from 0.1 to 10. That feels like, to me, you're going in the wrong direction. The calculator or MATLAB doesn't care. It'll do as many as it thinks because its while loop criteria are met. While this is happening, which is your f of x's are not 0, keep cranking along. So normally, if you don't set an iteration counter to even 5 for that matter, like I said, I think all the ones we've done, nothing's been more than 5, right? You just basically stop it. And the only reason why I suggest you stop it, that 10, is because you're running along and, you know, you get busy, you start it and you're like, okay, I'm going to, I don't know, take some notes or do something or whatever. and you're not paying attention, 10 minutes later, the thing is still calculating away. You didn't really gain anything by it. But if it flashes and stops after 10, and then here's the other thing, you check your results and say, these results make sense? Well, the first thing you do is I check N. What's my iteration count? If it's at 10 or whatever I stopped the iteration counter for, then I probably have a mistake. So I just go back in. And I don't even need to verify my f of x because I'm almost certain those are going to be wrong. So then I got to go back in and start to troubleshoot where I had a mistake. Okay. With your calculator, if you do one iteration for the test, that's fine. You don't need to do 4. So if you're using MATLAB, I want to see the full results. So here's the thing. If you want to play a trick and say like, oh, well, I'll just use MATLAB and I'm going to do one iteration result and get the answers. The problem is if you do 1 or if you do 30 in MATLAB, does it make any difference? Doesn't make any difference to you, right? You write a while loop, and then if you just crank it out after 3 iterations, if you give me the final results for your f of x or your x variables, it's no difference for you. MATLAB is doing all the work. You're just waiting for the results to be spit out. So it's not really a trick. You might as well just wait and run the iterations until it kind of spits it out. But if you're doing it by calculator, you're doing those all by hand. So that's why the expectation is just do 1 with your calculator and just give me the answer. It really is no additional work in MATLAB. Even if you said, hey, well, I'm not going to do a while loop, I'm just going to do it automatically. I had one student during a lab that actually did that. They did the iteration sort of manually, which is perfectly fine. All you do is copy paste for the new numbers, right? So it really isn't that big of a deal. And then we get this algorithm. Now we had to spend a little time, right? So there's a lot of little steps to make a load flow work. And the next probably biggest step is identifying the bus types. Because all I need to do is know the bus type to help me figure out what equations do I need to write, and thereby what variables do I need to solve for. So slack, load, gen, reference, PQ, PV. Slack bus, no equations. Because I know the magnitude and the angle of the voltage. I set it. That's my reference bus. But that's a good thing because I can't write a PQ bus. I can't write PQ equations at the slack bus because I have no clue what the power injected is supposed to be there. So I have no way of actually checking if my result is correct. So I'm gonna lock it in at the magnitude and angle. A load bus, I don't know magnitude and angle of the voltage at all. But that's okay because I can write a power balance equation, both the real and reactive power, which is as those variables are not known, I'll be able to check, are those correct at the PQ? Because I know what the power injected at those buses are supposed to be. A generator bus or a PQ bus is I specify the magnitude of the voltage, but I don't specify the angle, okay? But I do specify the real power, because remember, I'm operating the generator, I got so much steam or so much capacity, I'm gonna run that at 50 megawatts or whatever power you have. So I'm controlling the P, but I'm not controlling the Q unless I overload the generator. So I'm gonna fix that, I'm gonna allow the Q to be whatever it needs to be, which is okay, because I only have to have an angle for, I only have the power balance equation for the angle, which means I need the real power. Go back to our transmission line discussion. Remember how I said real power flow is based on the angle, theta, and reactive power is based on the magnitude V? Same thing over here. The power over here is going to help me determine what the angle theta is going to be. I don't know the Q. That's okay because I'm fixing the voltage, and so it adjusts up or down. And all of these bus types are necessary because I can't indicate or I can't specify what the system's going to be because I have no idea where the power is flowing. It's going to flow in all different directions as the system is operated. And so that's why I need those bus types. But there's only 3 bus types. And another check for you is when you go through the system, make sure you have at least 1 slack bus. Your entire system could be slack buses, but that wouldn't really do any good, right? But your whole system could be all slack buses, But if they're all slack buses, you wouldn't even do a load flow. So you got to have at least one load bus or one generator bus to be able to do the load flow, right? But as a minimum, you need one because you can't fully specify the system. So you always have to have one slack bus. And then you can have as many load or generator buses as necessary. Typically, in the real world, you have a lot more load buses than generator buses because it's not easy to specify the P at a bus. Unless like a cap bank where you know it's going to be zero, or if you have some other device where you can ensure it's zero. But again, you're trying to sell joules, right? So you want to sell power because joules are what you're going to get paid for. Kilowatt hours are what you're going to get paid for. You're not getting paid for VARs unless you have a low power factor penalty. So you want way more load buses than generator buses and slack buses. All right. And you don't have to have any generator buses. You could have a system with one slack bus and the rest are load buses, primarily because my reference bus is going to take care of all the P and the Q in the system. Maybe I've got 10 generators connected to this bus, this one slack bus that I'll be able to provide all that. So yeah, definitely load buses are going to rule the rules. And here are the equations you write. I for sure would write these two down because there's no way of getting it. Up to you if you want to write the Jacobian equations down. Like I said, for the systems that we're doing in this class, as long as you're reasonably confident in doing partial derivatives, I find it faster and easier to do the partial derivatives. But that's up to you, your call. Don't forget, when you're doing these power balance equations, this G is a real number. This B is a real number. It is not a complex number. So do not include your J terms. I had one student reach out when they were doing the homework saying, why am I getting my Jacobian with complex numbers? That's because your B term, you included the J, right? Newton-Raphson algorithm can't handle complex numbers. So do not include J terms in any of the power balance equations. If you recall, we derived those in such a way so that we split up the P and the Q so that all the real parts ended up in the P and all the reactive parts ended up in the Q. So we've already sort of equated each of those to make sure all the J terms are gone. No J terms whatsoever. And then the last is just some questions. Transmission line loading, right? Basically say surge impedance. Calculate some line performance like efficiencies, power loss, voltage drop across a line, voltage regulation across a line, that type of stuff, like how much the voltage is going to change. ABCD parameters. Use the medium length line, right? We already talked about that. Nonlinear equations, Newton-Raphson. Be able to do that, show you work. What about what it takes to do a power flow? Like if I had a 10 bus system that had, let's say 8 load buses, one generator bus and one reference, one slack bus, how many equations would you need to write? How many variables would you need to solve for? How big would your Jacobian matrix be? What would your Jacobian matrix look like? The partial derivatives, right? So maybe not necessarily actually doing a 10 by 10, a 10 bus load flow. Because again, how long would you all have to do 10 buses? Most people now, said some people said it took 7-8 hours to do homework problem number 2. So if we went to 10 buses, what is that, 30-40 hours? Too many for a test. And I don't actually want you to do that either, because that doesn't demonstrate knowledge. That just demonstrates you can grind through material. That's not what I'm interested in. So being able to go and take the knowledge that you've hopefully developed and actually make it so that it's a reasonable result in getting your power flow, that's what I'm interested in. So specifying the effort means you understand what you're doing. Not can you do it necessarily, because again, if you ask me to do a 10 bus system with that many buses, I can guarantee you I'm going to make mistakes on the first pass, 100%. And I've done a lot of these. You can ask industry experts to do it. They probably couldn't even do a load flow by hand. They would say, where's my PSSE or SKM or whatever to do it, but that's okay. They've got thousands of dollars to spend on software. We get MATLAB for free. And then do a load flow in a simple system. 2 bus, 3 bus, that's what I consider simple. And if you can make some assumptions, it might make it even easier, right? Like there's no G. That type of stuff. That's it. Questions? Yes, sir.
What do you advise us to look at for practice? Because I know that the most recent one we have like
Yep.
that's we would do that, just like class notes and previous homework.
Class notes, previous homeworks. If you look at the Shomes outline series, that would be okay to look at practice. Just be careful because the Shomes outline, there's a couple ways to set up these power balance equations. Like they don't have to exactly look like this. So sometimes they use slightly different approaches, but just be careful while learning a different approach. It might be confusing, but it's still using Newton-Raphson algorithm, but their power balance equations just look a little bit different. But the Shomes outline, that was the one I recommended at the beginning of the summer. I mean, at the beginning of the semester, about $20. That usually has some pretty good examples. Again, I would like I said, for me, when I would study for classes, and this is mainly in grad school, I would just rewatch the videos and make myself notes because I was trying to understand the methodologies or the approaches as opposed to just cranking through a problem after problem. This isn't circuit analysis 101, where you're like, okay, you're going to do 55 mesh equations so that you can do it backwards, forwards, inside out. This is like, okay, do you understand the concepts and the methodology to do it? So that's how I would study for this. Make yourself lots of notes because if you can explain it to yourself, write it down so it's coherent. That extra step usually is what would work for me. So I can only give you specifics of what worked for me. You all have your own different studying styles, but that worked really well for me is being able to explain to myself. And if you could work with a partner or two, and you can explain it to them, even bigger thumbs up. Because you're explaining it to yourself, and sometimes you kind of put words in there that aren't necessarily there. But if you're sitting next to your partner and he's asking you questions, you're explaining to him, he's like, what? What did you just say? It forces you to go back and then restate it, and then that hopefully helps it get clear. What else? This is probably going to be the most difficult material you'll have in this class is the Newton-Raphson. Yes, sir.
For the Newton-Raphson and the load flow, like homework, for the iteration, if you just want to write the equation and then do the one iteration.
So
like that,
if you're doing it on your calculator, just one iteration.
if you are using that left.
Give me the final answer. I don't even care about that. Final answer. It should be in the ballpark, right? Because you should be trending towards the correct answer.
Right.
So if you gave me numbers of an angle of 82 degrees, 37 degrees, and a voltage of 1722, you're probably not trending in the right direction.
Right.
But if you're around where you expect it to be, that's fine. Yeah, and I don't care about how many iterations MATLAB does because that could just be your precision. If you wanted to be, 1 times 10 to the minus 12, you're probably going to have a few more iterations in there. I'm not that interested in that.
So really just for putting on the correct equation.
Putting in the correct
Yeah,
equations,
somewhere.
putting the numbers in the right spot, making sure your calculators are in radian mode, not degrees. Because I don't know, nobody else, I think most people heard that because I said that very emphatically at the beginning of this material. If you try to do this with your calculator in degree mode, they never converge. I've never seen it converge once. But if your calculator's in radian mode, it usually works pretty well, as long as, again, you haven't made any errors. That's another advantage of MATLAB because it only has radian mode, right? So you're forced to use radian mode. Yeah, as I was saying, this is, the concepts are tough. And for most of you all, this is probably the only time as an undergrad, you'll have to solve nonlinear equations on paper. You can't just look at a plot or a graph and linearize. You've got to go ahead and do it. There's no plot that you can envision that has maybe 1 million different dimensions, right? Things would be crisscross. It would just not be practical. So Doesn't work that way here. But hopefully now you're pretty comfortable at it. It's not that scary. Yes, sir.
So for that part, once we have kind of our matrices set up showing how we get our delta whatever value, the error that we're trying to get to zero, then for showing our work could be right after those equations iterated through MATLAB to get final value.
If you want, or you can just give me the final values. I'll assume, maybe this is the big assumption, but I'll assume that you did not do 3 or 4 iterations on your calculator. I mean, if you give me answer that these are the final voltages, that's my assumption. You're welcome to do it on your calculator, but these gentlemen said it took 2 hours per iteration. So probably not the best use of time. But with MATLAB, like I said, it just 3 seconds.
So that's sufficient for showing the work.
No, you're missing my point. The iterations I don't care about. The Jacobian I don't care about. I want to see the equations that you're going to put in your Jacobian. I don't actually care to see the numbers. I just want to see the equations. V2 times sine of theta 2 minus theta 3 plus V2 V3 times sine of theta 3 minus, whatever that is. Those are the equations I want to see. I don't need to see the numbers. I just want to see your end results from each iteration. Yeah, and that's the thing too. If you're doing it with your calculator, if you want, you're welcome to show it, but I wouldn't even bother on my paper that I'm turning in showing what the Jacobian looks like with the actual numbers. Because again, that's just busy work. You're going to do that until you get the right answer. All I care about are my X values, my variables that I'm updating, and my f of X. Did those equal 0? So that's way less than doing a Jacobian. Anything else? Feel good? Get the weekend to work on it. Tropical storm or hurricane is coming our way, right? It's supposed to start raining tonight. Crazy winds.
Really? I thought it was going off to sea.
I heard we're supposed to have like 30 to 40 mile an hour winds in Bangor tonight, but maybe I'm wrong.
Let's cancel the exam.
Let's cancel the exam. Well, the exam is Monday, so.
Hey, yeah.
All right, no problem. We'll just make it up on the final. So your final grade will be worth 35%. How's that?
Hell no.
We've got to equal 100%, right? I mean, hey,
That's what
I'm willing to accommodate as best as I can, but there's a lot of chips are on the table when you're doing 35% of your grade.
Hell.
The joke is everybody hates doing prelims and all that stuff. But the reason why I like to do 3 prelims and a final is it takes a lot of the stakes off. If you had a bad day, not feeling well, that one prelim is not going to say you failed the class. But if you do a midterm and a final, boy, oh boy. In grad school, we typically would just do that midterm and a final. And there's a lot of pressure on those. So we actually do it to be nice, not to be mean.
Hey, Paul, I had a question.
Yes, fire away.
So it's kind of specific. I also sent one in chat that's separate, but
Oh, I didn't see it.
no worries. So chapter 6, on class 1021, slide 16. I know it's very specific. You have a Jacobian value for your x1, and I'm trying to get in some practice, and I haven't been able to figure out how that number was, like where that came from. I just need to understand the process. Slide 16. So it's your 2-bus example.
Slide 16. Which was it the Newton-Raphson load flow, or was it the 2-bus with X and Y equations?
It's the 2-bus Newton-Raphson example with just your basic Z-line. So it says chapter 6, page 35 through 56, is done on class 1021.
All right, hold on. No, it's not this one.
Yeah, that one.
Tell me when you see it.
It should be 16. Yeah, it's that example, so keep going. Next one. Okay, so you have on the second line down the JX1, the 8.82.
Yeah.
Like I was trying to get in more practice, but I couldn't quite figure out like where that came from, and I wanted to get that process embedded, but
Yeah. So this is my Jacobian, right? My generically written Jacobian, 10 V2 cosine theta 2, et cetera, et cetera.
Yep.
If you plug in 0.212 for theta 2 and not theta 2, yes. So if you plug in, not 0.212, if you plug in negative 0.2 and positive 0.9 for theta 2 and V2 respectively into this equation right here, 10 V2 cosine theta 2, you should end up with 8.82.
okay.
You want to do it
Okay.
here?
I wouldn't hurt.
Sure. Let me bring it up. Like I said, I'm just going to use my calculator. And I've got, let's see. Everything's on this page. So I've got, I'll call it theta 2 is equal to minus 0.2. And V2 is equal to 0.9, right? So now my Jacobian for position 1, 1 is 10 V2 cosine theta 2. So 10 times V2 times the cosine of theta 2 should be equal to 8.82.
3 times.
Yeah, I need my times here. That's where you get it from.
Okay.
It's your next iteration result. So I have to update my f of x and my Jacobian each time I get updated values for my variables, my unknown variables.
Right. Okay. Okay, no, that definitely helps. So I'll get the rest of the process. And then yeah, in the chat I sent you, you said I equals 2, and we have the so the subscript for our power balance equations. K equals 1, I generally equals 2, but when you look at the equations when they're built, a lot of the times it's really just referencing like where in our matrix our values are. So I was kind of getting a
No,
little
that's
confused.
that's different. So you're talking about, let me show you what I mean. I think I know what you mean. So when I do my power balance equation, this is I, and then I have a summation, K equals 1 to N.
Yep.
Let's say that this is VK sine theta IK, right? So the I and the K that I'm talking about are here and here, right? That's
Yep.
the I term. And then K is going to be here and here. But that varies. The K goes from 1 all the way to N. If I did my Y bus of I comma J, that's the elements of my rows and column inside my Y bus. So that's an actual physical, not physical, that's an actual matrix location. Where over here, I'm actually doing a math summation to get those parameters. So I'm pulling out, let's call this GIK. I'm pulling out wherever that physical location is in the matrix and then putting it up front. All right.
So does that then essentially have no impact on the values we have as a result? Is it more of helping you keep track of where you are in building your equation?
I'm not quite sure I understand the question. Can you restate it?
When you have those subscripts and you're building out your power balance equation, the
Yeah.
subscripts for I and K, they tend to not have a mathematical impact, or is that an
Oh,
incorrect
they
assumption?
definitely do. They definitely do, because it's telling you the numbers that you need to put in. So this number here, maybe it's a 2. So everywhere you see I, you substitute in 2. K is going to go from 1 to N. So you pull those values out based on location. So this would be, let's start with 1. This starts with 1, and then the next iteration, it moves to 2. Over here, this is going to go 2, 1, then 2, 2, and on. But then you have to pull out that value from your Y bus. The G and the B, you got to grab it from your Y bus. The other terms, you're just gonna mathematically add them so that you know what they represent.
Okay, so if VI represents V2, then
Because
obviously,
PI is defined right here, right? That's where we define it. So it's delta PI. If I'm writing a power balance equation for delta P2, then I know for certain that I is going to be equal to 2.
okay, so then that's where if you have your 3-bus system, you have a slack bus, so you have like P2 and P3, then I will obviously just correlate with what you're searching for.
Correct.
Okay, okay. All right, thank you.
Sure.
So then B for like. That would be the B part of the Y bus, being slot Q1.
In row 2, column 1.
Yeah.
So slot, you said slot, but I just want to be clear because sometimes with matrices, and again, it's just like how engineering has evolved. We don't do enough with matrices, but it's rows by columns, right? So I don't like to say slot. I just want to go, it's in row 2, column 1, because it just gives you an exact map location. Anything else? Feeling a little bit better than good before, right? You wanted to cancel the test. Now you're okay. Yes, sir.
One last thing I think of, when we're writing that out, whenever we come across that, for the real power equation, that sign term that cancels out to 0, which always happens, because you have, when your K is equal to your I, you're gonna have
Yeah.
a sign of some angle minus that same angle.
Yep.
Which is sine of 0, which is 0.
Yep.
Do we have to write all that part out?
If you want to skip it in your first one,
If it, and
that's fine. I don't know that there's a huge time saving to ignore it unless you're really efficient at it. I probably would just write it out the first pass, but then when I try to clean it up and make it a little more simplistic, then I would say, I know that goes to 0. So that's just a way, like for me, again, it's more meticulous and then I can actually check. Yeah, I have that one there. I didn't skip it. It goes to 0. So then I just take it out. But if you know it's the same one, you can write, it doesn't exist. You can skip over. That's fine too. It doesn't bother me. But again, if you try to do a lot of shortcuts, sometimes you actually add a lot of risk because you're like, whoa, what's going on here? This doesn't look like I expected to. And then you start overthinking it. I made a mistake and all that stuff. It's like, if you just keep it simple, sometimes it's better to do it that way. But you can do either one. I don't have a problem with that.
I forgot the minus when I removed the I, the sign will go to 0.
Yep.
I skipped it. And then B is minus B. Forgot the minus on the B.
Now, how many hours did it take for you to find that?
Long times. I forgot about it. So
And B is a really meticulous person and he just forgot one little thing. And it's like, oops. That is, again, the hard part about this, right? It's easy to make mistakes. Anything else? All right, you get an extra 25 minutes. Get right to studying. Get on it.
go to Chem Lab.
Or go to Chem Lab. All right, y'all. Have a wonderful day and weekend, and I will see you all next Monday. Take care, everyone.
Thank you very much, Paul.
Thanks,
Thanks.
guys. Thank you.
See you, Paul.
See ya.
Hey, Paul.